welcome back to this NPTEL lecture. Again we will be continuing with this wear behavior of bioceramics and biocomposites. In the last lecture I have given sufficient introduction whatever of relevance to this particular NPTEL lecture on tribology. So, here I will present another published case study from our own group, and that is on the glass infiltrated alumina. So, just to refresh your memory, this is that various physical and biological properties that need to be considered for an implant material, like processing, like what the processability to make complex shapes, CAD/CAM designing to produce desired shapes and porosity, microstructure like microporosity and macroporosity, physical properties, lower density elastic modulus, in vitro biomineralization, electrical properties, in vitro biocompatibility, antibacterial properties, and in vivo biocompatibility. So, some of the things I think at certain point of time in previous lectures I have mentioned to some extent. Okay. Now, what are the different aspects of the biomaterials, wear of biomaterials in simulated body fluid? Now, this slide summarizes 4 different factors. One is that SBF composition, ionic concentration, and serum protein. Now, in one of the earlier lectures I have mentioned that simulated body fluid contains different chloride salts, and there some of the metal ions like sodium, potassium are important. So, this ionic concentration is important. Now, in order to make the environment more aggressive, often people use 5 times or 10 times SBF concentration in terms of the SBF, 5x or 10x SBFs, essentially where the ionic concentration has been increased to 5 times or 10 times, and then serum protein. Second one, normally in some of the earlier case studies I have mentioned that it is possible to realize reduced coefficient of friction and less severity in friction in case of the wear of materials in simulated body fluid. Third one is surface property like hydrophilicity or hydrophobicity, and how biological reactivity in SBF that changes, that also influences the friction and wear. And fourth one is very important, that is size, shape, composition, and amount of wear debris particles. I think I have mentioned very categorically that this shape and composition of the debris particles as well as size, they influence the inflammatory responses in the physiological body environment. So, one of the case study I must mention here in this particular lecture is a glass infiltrated alumina. So, alumina is one of the bioceramic materials, but it is mostly bioinert materials because it does not have that much bioactivity like hydroxyapatite, for example. But where glass infiltrated alumina, this can be used for dental applications, for example. So, as the name suggests that that you can use these normal glasses, Pyrex glasses, which is used for coating substances, and you can have 99.5% purity alumina, which has a coefficient of thermal expansion of 9.1 10 to the minus 6 Kelvin inverse, and these are the standard numbers for elastic modulus and density. Now, when you use these two type of materials, one is the sintered alumina and another one is a glass infiltrated alumina. So, AS is the as sintered and AG is that alumina glass infiltrated materials. So, there is an increase in the flexural strength, and this increase in flexural strength must be because of the compressive stresses that are generated on the glass infiltrated alumina because of the glass infiltration. Vickers hardness increased to some extent from 18 to 19, 17.6 to 19.2. Indentation fracture toughness, there is a very modest increase from 3.9 to 4.6, but if you look at the error bar, I think it will be overlapping. Now, for any new materials, we always test at different loading in the fretting wear tester. In the different loading, like we vary the load like 2 to 10 Newton in load for both alumina glass and alumina sintered alumina, and then what we do, we vary the number of cycles. For example, if you look at this particular case, that is the number of so we can see that that number of cycles is varied from 10,000 to 100,000 for alumina glass and alumina sintered, and then you can see that how where it is changes. So it goes from 10 to the minus 4 to 10 to the minus 6. So that means wear it reduced as you increase the number of cycles. And coefficient of friction, it almost remains similar or there is little bit decrease 0.63 to 0.54. The same thing you can see 0.56 to 0.49, like 0.56, 0.5 to 0.49, that coefficient of friction is also reduced. So this is one of the representative plots for the number of coefficient of friction or frictional evolution with number of cycles, and this is for the AS, that is that alumina sintered, and this is for AG, that is the glass infiltrated alumina. So what you clearly notice that at the higher the load, that coefficient of friction steady state is established relatively faster and it is maintained. There is not much fluctuations. These fluctuations normally we have observed at the lower load like 5 Newton as well as 2 Newton, but at 10 Newton load it is all stabilized, and the coefficient of friction in both the cases alumina sintered and glass infiltrated is 0.5 or less than 0.5. And this is the case for the steel as a counter body. Okay, this is the case for the steel as a counter body material, and that whatever data we have presented in the table, and then you can see that how the plot is also when they are plotted against the load. So for glass infiltrated alumina, this wear rate is reduced, but at 10 Newton load it is comparable. So where it is reduced with load, but what you observe in case of this as sintered alumina, the wear rate is also reduced, but the wear rate between these two materials for both this glass, this is for the AS and this is for the AG. For the AG material, wear rate is lower at 2 Newton load and 5 Newton load, but at 10 Newton load they are more or less comparable. Okay. So this is the bright so this is the backscattered electron imaging which we have captured using scanning electron microscope of the wound surfaces. Now if you look at the first row of the images, what you see that first one is a 2 Newton, then middle one is a 5 Newton, and this is the third one is a 10 Newton. So this is the topographical features on the as sintered alumina after the fretting test for 100,000 cycles. That is the at the end of the 100,000 cycles we have taken these images. What you notice that there is clearly a signature of this tribochemical layer formation and also this abrasive scratches, which is somehow is reduced because of the extensive tribochemical layer formation, and there is some observations of cracking also at the 10 Newton load. Now if you look at this glass infiltrated alumina, this is the AG and this is for the AS. If you look at the glass infiltrated alumina at even in the 2 Newton load, which is very small load, there itself you can see very bright contrast area. This is the tribochemical layer, and at 5 Newton load this tribochemical layer formation is clearly visible, but much less. But at 10 Newton load you can see very thick dense tribochemical layer formation, which really appears in a different contrast. What it means is that this tribochemical layer has a different chemistry compared to that of the unknown surfaces. That is why they appear in a different contrast. Other things, if you compare this AS versus AG, again the contrast of the tribochemical layer is qualitatively similar. What it means, again like in AS, in case of AG also tribochemical layer with different chemistry that forms. Now therefore it is important to know what is this tribochemical layer or what is this wire debris chemistry. We have conducted the X-ray diffraction. So this is that XRD patterns where intensity is plotted against the 2 theta. And what you notice here that there are phases which are formed, this is Fe to SiO4 and FeOH 2. So, these are the phases which are formed as a result of the tribochemical reactions. So, you have a steel from the counter body, and steel is also reacts with SiO2, and plus in the humidity you can put is that H2O. So, then it can form is that FeSiO4. Okay. So, now these are the kind of potential reactions that can take place, and steel also can be this hydroxide of iron is also can be formed, because these materials are fretted against the steel counter body, and this is the case for the Ag, not As, that where is a glass infiltrated alumina. But the X-ray peaks are quite sharp, essentially showing that this phase which is formed at this particular after the friction fretting wear of these materials, they are essentially crystalline phases. So, this crystalline iron silicate or Fe2SiO4 and hydroxide both are forms after the fretting at 2 Newton load. So, let us now switch to another material systems where we have done also some study, and that is hydroxyapatite mullite composites. So, why hydroxyapatite mullite composites? Because hydroxyapatite is a bioactive material, but hydroxyapatite does not have good physical properties in terms of the hardness and strength. Mullite is a solid solution of alumina and silica. So, essentially mullite has a typical composition of 3:2, 3 alumina and 2 silica. So, it is a solid solution of alumina and silica in 3:2 ratio, and when you add mullite to hydroxyapatite, we are expecting that there should be an increase in the hardness and strength of the material. This enhancement of the hardness and strength is equally important, because for the tribological applications, if the wear is dominated by abrasive wear, then the increase in the hardness can lead to better wear resistance of the materials. Now, again we have done the different we have used the different flat materials, or where we have varied the mullite content like 10% mullite, 20% mullite and 30% mullite. For reference, we have used both the hydroxyapatite as well as the mullite flat samples. Now, what you notice that after the fretting wear, add the simulated body fluid, in the simulated body fluid, this is the 2D surface profiles of the region which experiences maximum wear. The top one is the hydroxyapatite without any mullite. Next one from the top is that hydroxyapatite 10% mullite, then 20m means 20% mullite, 30m means 30% mullite, and then last one is that pure mullite. So, the left panel is essentially for ambient environment, right panel is for simulated body fluid environment. Now, the scale for all these along the y axis, which indicates the depth of this profile after using different kind of materials, that scale is quite different. So, for example, if you look at the first one, it is essentially 20 micron is the scale. The second one is it for 10 micron, this is again for 20 micron again, and this lower one is a 4 micron. So, mullite as expected, mullite is because mullite is much harder. So, even for this third one is also for 6 micron. So, second from the bottom, here again the scale is 6 micron. So, while qualitatively you can see that there is wear scare and there is lot of hills and valleys in this particular wear profile, but quantitatively the wear depth is certainly different, and this wear depth, the difference in the wear depth can be ascribed to that difference in the hardness of the materials. As I said before, that wear mechanism study is of central importance in the for material scientists who work in the area of tribology. So, we always do this scanning electron microscopy investigation or transmission electron microscopy based analysis of the wear debris or wound surfaces wherever it is possible. Now, if you see that first panel, the top one is for hydroxyapatite, which is sintered at 1200 degrees Celsius after the wear is over, after testing against zirconia after testing zirconia ambient conditions. The second one is that HA-20M, that is 20 mullite. Third one is that HA-30 mullite, that is after sintered at different temperature, like one is 1200, the second, third one is 1350 degrees Celsius. What you see in the hydroxyapatite case, you see that there is a regions of exfoliation, and this exfoliation is very typical of some of the brittle materials, because hydroxyapatite has a fracture toughness of less than 1 MPa square root meter. So, it is much brittle than that of the alumina, because alumina fracture toughness is around 3 or little higher than 3 MPa square root meter. So, hydroxyapatite is extremely brittle. The second observation is that after testing with hydroxide 20% alumina, you can see that large region of the wound surface is fully covered with the tribochemical oxide layer. And this, if you look at this particular region little bit closely, you will see that there are wear debris particles which are being entrapped on this particular wound surface. Now, the formation of the tribochemical layer is also equally observed after testing in hydroxide 30% alumina, and here you can see the signs of delamination. But here there is a very dense tribological layer and wear debris that is formed on the wound surfaces. Now, this is so the last one is in the ambient environment. Okay. Now, one would be very interested to see how does this wear mechanism change in the simulated body fluid medium containing the albumin. And simulated body fluid medium, you can see that have 20% alumina, have 10% alumina, have 30% alumina pure mullite. And what you notice that here also there are signs of delamination, cracking and tribochemical layer. In pure mullite, it is simply that abrasive wear. Okay. So, whatever you see 10% mullite, 20%, 30% mullite, that these changes in the wear mechanisms must be attributed to the presence of other phases rather than mullite, simply because mullite, when they are fretted against zirconia in simulated body fluid, they only show abrasive scratches. So, the presence of mullite in the composites can be attributed only to the generation of abrasive scratches. Whatever additional observations one can notice from this particular SM image, this particular SM image must be due to the presence of any reaction phase which is formed because of the interaction between hydroxyapatite and mullite at the sintering temperature, that would additionally influence to the formation of the tribochemical layer. Now, this is how the that what we have published little 4 or 5 years ago, that what is the tribological properties, that summary of hydroxyapatite based materials. What you notice here, that along this leftmost column here hydroxyapatite based materials are there. What is the counter body? High density polyethylene, then zirconia, then glass infiltrated alumina. What are the medium of testing, that either plasma or bovine serum or ambient environment or SBF or water. Now, if you look at the coefficient of friction, most of the cases the coefficient of friction in these cases is 0.1. So, coefficient of friction is less than 0.1. Wear rate, it can vary 10 to the minus 5 to 10 to the power minus 9. So, depending on what is the material, what is the simulated body fluid composition, you can get where it varies between 10 to the minus 5 to 10 to the minus 9 millimeter cube per Newton meter. Wear mechanisms, it is fatigue wear, deformation and fracture, mild ploughing or delamination or abrasive wear. So, this is the total summary of what we have observed for the tribological properties of these hydroxyapatite based materials. Now, there are also evidences of that phase transformation of this zirconia, particularly after the fretting wear. Often tetragonal zirconia transforms to orthorhombic zirconia and so on before they go to transformation to monoclinic zirconia. So, this is the bright field transmission electron microscopy images of the polycrystalline wire debris particles, where you can see that inset is the characteristic electron diffraction pattern, and you can see this nanoscale crystalline structure. But here this is the some of the work by Mitch and Carlin, where you can see very amorphous debris formation. So, amorphous debris formation, it is clear from the diffuse ring. So, if your selected area diffraction pattern, if it is a diffuse ring, then it is amorphous debris pattern, and this is for the crystalline P, because this is a spot pattern in the selected area diffraction pattern. So, TM analysis actually is very useful, because in the transmission electron microscopy images you can get this selected area diffraction pattern from the very localized region. And if you look at the other contemporary measurements, for example, scanning electron microscopy or X-ray diffraction to some extent is possible, Raman spectroscopy and so on, it is very difficult to confirm with greater assurance that these debris particles are indeed crystalline or amorphous, but TM actually gives you very clear idea about the nature of the debris particles. Now, if the debris particles are crystalline, which is the case for many of the 3 body wear situation, and then they can contribute to the further wear depending on the hardness difference between the debris particles and one of the matting solids, then it will cause wear of the softer of the matting solids. The same thing is true for the debris particles in case of the amorphous, but amorphous materials, because they do not have the crystallinity. So, in the amorphous case it is quite unlikely that they will cause lot of wear. However, under stress in the frictional surfaces, often amorphous wear debris particles can undergo crystallinity. So, before I finish this particular lecture on the wear behavior of bioceramics and composites, it is not only the bulk materials, but also researchers use various surface coatings. For example, you can have titanium materials, but you can put this surface coating on the titanium, for example, DLC, diamond like carbon coatings. But this is the case for the friction and wear properties of some of the titanium based materials without any coatings. And here you can see that there is a series of titanium based alloys which are of relevance to clinical applications. For example, titanium 13% niobium, 13 zirconium, or Ti6Al4V, which is extremely widely used, or titanium 5% aluminum, 2.5% iron. Now, this titanium alloys actually is an area which is very extensively pursued by the metallurgists, and metallurgists they used different alloy design approaches to bring in some of the outstanding properties in the titanium based alloys. And these 3 alloys are just some examples, 3 examples from this very large pool of the titanium based alloys. And when you see that when their frictional properties are compared with their commercially pure titanium, depending on the alloying elements addition or depending on the alloy composition, it is possible to realize a much reduced coefficient of friction. For example, if you compare with a titanium 5% aluminum, 2.5% iron, one can get a coefficient of 0.3, and this is the 0.3, but when at the commercially pure titanium it is around 0.5. So, there is a clear and distinct advantages of using the titanium based alloys in biomedical applications, because one can bring down the coefficient of friction from 0.5 to 0.3. When compared to the titanium based alloys, another materials which is used for orthopedic application is the cobalt chrome. So, cobalt 28% chromium 6% moly alloys, and this is used for the knee replacement applications. And these knee replacement applications, if you see that again their coefficient of friction is fairly close to 0.3 to 0.4, or it is little less than 0.4 against steel as a counterbody materials. As I said before, that one can use that diamond like carbon coating or titanium nitride coating and so on the orthopedic bearing surfaces to reduce force of friction and wear. So, this is just an example that these diamond like carbon coated cobalt chrome moly alloys after coating, without coating and with coating. So, this is that on DLC coated cobalt chrome moly. So, this is 10 at 10 Newton load 10,000 cycles. This is the coated surfaces, okay. This is not uncoated surfaces. You see that there is signs of these debris particles here, but there is some scratches, but you do not see any underlying surface. But at 100,000 cycles, what you see, this white contrast, this is like underlying surfaces. What it means that this coating survives this coating can survive only less than 100,000 cycles. After 100,000 cycles, you can clearly see that coating gets peeled off, or coating gets abraded away, exposing the underlying surfaces towards the wire, which is not desirable. So, these kind of fretting wire experiments essentially are very useful to also quantitatively evaluate the durability of these coatings under tribological conditions. Now, this is also another thing that one can understand, that it is not only understanding the friction and wear mechanisms for tribological surfaces, but also it is important to know what is the stability of these coatings under the tribological conditions in terms of the time scale. So, that if the coating is gone, then the underlying materials can lead to much more severe wear. So, with these examples, I think I end this particular lecture, and I will come back to the next lecture and this NPTEL series. Thank you.